Recorded is rolling. It is Tuesday, January 17th. Welcome back from a 3-day weekend, Martin Luther King weekend. So we're going to do a Kahoot on just waves. Don't worry about sound, just my other class. Right. So do Kahoot on waves. 20 conceptual questions here. We've just got a few questions left for from chapter 15. So we'll wrap those up. That'll take us to the end of class today. Tomorrow I have a Speed of Sound Lab lineup for you guys. Actually, one of the questions on your chapter 15 homework is going to be really similar to lab tomorrow. It's called tuning forks, PVC pipes, speed of sound. Okay. In-class quiz on Thursday. This will be open notes. So any notes you guys took in the past, take today, take tomorrow. There have been a few labs last week and also tomorrow. All right, labs. If you guys want to use your homework on your quiz, that could be part of your open notes. Right? Then I have a few ideas for Friday, so we'll see by the time we get there. But open notes quiz on Thursday, and then I'll pick up your homework Friday. And so switch screen over here to Kahoot. All right. Hey, you guys are logged on there, so thank you for hopping on Kahoot. Give you guys a few more seconds here. Can you grab that pin? So all these questions are going to be on waves and wave motion. Maybe periodic motion. Might be some pendulum questions in here. Well, let's get started. The time needed for a wave to make one complete cycle. The time needed. Oh, yeah. Yeah, is one time period that you can count in some number of seconds. Now, the distance that corresponds to that is called one wavelength. If you think the right one, so it's related, right? So a wave will travel a distance of one wavelength in one time period. Right? If you take the reciprocal of time period, that's the frequency in hertz. Sound. Sound is what kind of wave? Yeah, longitudinal wave. You guys remember longitudinal waves? It could be like a pressure wave, compression wave. If you stretch your slinky across the room like I did last week, and you pull it and just let it go and it goes pop, it sends a little compression wave back and forth. Right. Now that's in contrast to a transverse wave, which is easier to draw. It's like if you shake the slinky up and down, it's like a classic S shape is the transverse, right? But sound is like a pressure wave, like longitudinal, which is kind of hard to draw because you have to like draw a bunch of like air molecule dots and all that. All right. When two or more waves, same place, same time, resulting effect is called? Right, interference. You guys remember constructive, destructive interference? Got a couple posters up here, right? Got interference patterns. You guys remember that? You can add the amplitudes together, right? If got positive, negative amplitudes, they might like deconstruct it possibly. Constructive and destructive interference. The amplitudes. Where can you touch a standing wave on a rope? Talking about transverse wave, standing wave, without disturbing the wave. At a node, right. You guys got that. Right, you guys see this poster right here? Is it the red apples, I think, are the nodes. Right, you guys see this? Right. And so now that's only true for a standing wave, right? Transverse wave, standing wave, right? And I made one of those. You guys remember stretch the slinky across the room? Set up a transverse wave and you shake it just right. There could be a point like right in the middle that does not move. That is the node. Standing waves can be set up. Yeah, all the above. Those are true. Right. Now, those are different types of waves. Like the red and blue ones would be longitudinal waves because those would just be straight sound waves. Right. If you're talking about the string of a musical instrument, that probably has more of a transverse type motion. which would push against air molecules and create a resulting longitudinal wave. But yeah, but they could all be standing waves, just different kinds. And tomorrow in the lab, got a tuning fork PVC pipe. It's going to be more like these top two sort of. Suppose bug jiggling up and down, swimming towards you at the same time. Compared to the frequency that the bug emits waves, the frequency that the waves reaches you. You guys see that picture there? It looks like the Doppler effect. That is a higher frequency. So if the bug is just flipping up and down, maybe the bug in the water is going like blip, 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 and sending out ripples in all directions. But if the bug is swimming, say, towards you at the same time, those wave crests hitting you is more like blip, 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 blip. It's going to be more frequent, right? More frequent. It's the Doppler effect. All right, so this is about to be the same scenario, a little bit different question. So same scenario compared to the speed at which the bug is emitting waves, the speed that the waves reaches you. Ooh. Ooh, a couple of guys remember. So remember, the speed doesn't change, right? Once that wave has been emitted into the atmosphere or into some medium in general, or maybe into the water in the case of bug with ripples in the water, right? Those waves just travel at whatever speed they're going. They don't really care about the motion of the source or the observer anymore. That doesn't matter, right? The speed of sound through some medium is just whatever it is, right? Now the frequency observed can be different, right? If you're talking about like how often do the crests like blow up against the shore or something, right? But yeah, speed is just whatever it is, right? That didn't change. Frequency can change, wavelength can change, but the speed is just whatever it is for some particular medium. As the sound of a car's horn passes and recedes away from you, the pitch seems to decrease. There you go. Right. I got a poster over there for Doppler effect. I think we ran one or two of those last week. Right, we're trying to navigate the plus or minus. Right, so who's moving, the observer or the source? Is that going to result in a higher or lower frequency? Therefore, do you have to do the plus and minus? Kind of a logical approach to that Doppler effect right there. You guys got the formula for it hanging on the wall. The Doppler effect is the change in observed frequency due to motion of something. It could be the source emitting the waves, could be the observer, right, listening. Right? So somebody has to be moving back and forth, or back or forth. Right? Somebody has to be on the move. If you double the frequency of a vibrating object, its time period does what? Yeah, it gets cut in half. Right. So give you guys an example right here. Suppose you go. Right, were you guys hearing 1 beat per second? Could you guys call that 1 hertz? Right, because 1 beat per second is 1 hertz, right? In the time period between each beat, well, you take the reciprocal 1/1, so 1 second between beats. Right. What if I do this? I think it's pretty close to 2 beats per second, which would be like 2 hertz. Right, that's a frequency of 2 hertz. And how much time between beats? Half a second. Right, reciprocal. Right, that's it. During a single time period, the distance traveled by a wave is one wavelength, right? So a wave will travel 1 wavelength in 1 time period. In fact, if you divide those two, 1 wavelength divided by 1 time period, you get the speed of the wave, meters per second. Yeah. Child swings back and forth on a playground swing. They stand rather than sit. What happens to the time period of that swing? Ooh. Okay, yeah, so the time period would decrease. Another way to say that is that it's gonna swing back and forth faster. Okay, okay, let me switch my screen over here and show you guys why. Okay, so you guys remember about a week ago, you guys had a pendulum lab, you guys came up with this expression. So here's the time period of a pendulum, how much time does it take to swing back and forth? Okay, here's how long the pendulum is, here's the gravity field of the planet. Okay, so it all fits together like that, right? Okay, so we're comparing these two scenarios. The first one, this kid's gonna sit down. Ooh, so it swings back and forth. It looks like our control situation, right? Okay. In the second scenario, now he's going to stand up. You guys see if he stands up, his center of gravity moves up, center of mass moves up, which effectively shortens the length of the pendulum. If you have a shorter pendulum, this numbers get smaller. Everything else stays the same. Gravity field's the same, though, right? So this gets smaller. This all gets smaller. The time period gets smaller. It's shorter. So here's the kid on the left. Swing, 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 swing. Here's the kid on the right. Swing, 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 swing. Right? Suppose simple pendulum suspended in an elevator. When the elevator accelerates upward, what happens to the time period? Ooh, couple of you guys got that. Yeah, the time period would decrease. That's to say it's going to swing back and forth faster. Right, here, let me switch my screen over and point out why. Think about this. Okay. All right, so here's the time period of the pendulum. Time period is 2 pi times square root of L over G. Okay, so we got that. Okay, so you're sitting in this elevator, everybody's at rest, or constant velocity for that matter. Swinging back and forth, everything looks to usual. Right? Then the elevator starts accelerating upward. Ooh, guys, does this guy feel really heavy or really light inside this elevator? Really heavy. I think the scale's rating a huge apparent weight. Right? So he feels really heavy. Think back to semester 1. Could we sort of modify the apparent gravity field as like instead of G, it'd be G plus A sort of, right? That comes back from semester 1. We I think derived that a long time ago. Right? So think it's like a modified version. Right? So we're pumping up the apparent acceleration, apparent gravity field, which increases this denominator, which does what to this fraction? Makes it smaller. Right? And so the time period is also going to be smaller, isn't it? Right? So if it was just regular gravity, it'd be like swing, 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 swing. But in an upward accelerating elevator, it feels so heavy. Swing, 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 swing. Right? If you feel really heavy. Hey, how about this? What if you went the other way? What if somebody cuts the elevator cable? Whole thing, free fall. Right. Now what's that pendulum gonna do? It's not gonna swing at all, right? Because it'd be like floating around like an astronaut. You pull the pendulum up, you're just like, oh, it's just gonna float around. Right? Because that would be G. Guys, what's G minus G? 0. What's anything divided by 0? Like infinity, right? So it would take an infinite amount of time to swing back and forth. Say it's not going to swing back and forth in free fall. That's like the opposite of that question you guys just saw. All right. Back over to Kahoot. How you guys doing on point 2? All right. Observer on the ground hears a sonic boom created by an airplane flying at a speed. Yeah, greater than the speed of sound. That's called supersonic, right? Supersonic, greater than sound, greater than the speed of sound. Okay. You guys hear a sonic boom over the weekend? I think they were watching a rocket. Yeah. You guys got that poster over there. You guys see that supersonic plane? Right, you guys see that that cone shape? That cone shape from those sound waves? Ooh. Sonic boom. First control. Yeah. Sound wave that has a higher frequency has a wavelength. That is what? Yeah, shorter wavelength. Sure. Let's look at that real fast because this is an important wave formula right here. Speed equals wavelength times frequency. You guys remember that? Right. Actually, here, let's do this one. Okay, wavelength times frequency. Okay. All right. So, here, let's do some numbers. Speed of sound can be 340 meters per second. Hey, do you guys think that the from my voice to your ears, the sound wave, it's like a pressure wave traveling this path pretty close to you, right? Right. And let's say you were talking with like a low frequency of like 10 hertz. Think the have a long wavelength. But then what if I increase the pitch? Increase the pitch like 20 hertz. Does that make a shorter wavelength? Yeah. Did the speed change? Did the speed of sound change? No. The speed is just whatever it is, right? But a higher frequency is a shorter wavelength. Ooh, there's an inverse relationship between these two guys right here. Wahoo. Two waves, same place, same time, in step. Each has an amplitude of 1 meter. What's the resulting amplitude? 1 meter, crest to crest, in step, same place, same time. 2 meters. Ah, right. That's called constructive interference. That's this poster right up here. Constructive interference. 1 + 1 is 2, right? Just add the amplitudes. Right? You guys remember that demo from last week? Played you guys a demo. Those wave pulses actually pass through each other too. It's kind of an interesting thing. Alexis, back to the top. Weight on the end of a spring bobs up and down 1 cycle every 2 seconds. Ooh, you guys remember lab with the spring and the weight? What's the time period? 2 seconds to bob up and down. So the time to bob up and down is 2 seconds. Ah, you guys got it. Yeah, 2 seconds. Okay. Now, if you pick the red one, you were probably thinking not the time period, but the what? The frequency, and the frequency, the unit would be a little bit different too. The frequency is 0.5 what? Hertz, right? Hertz is like cycles per second, right? So the time period is 2 seconds, and the frequency would be 0.5 hertz. Okay. Leaf on the pond bobs up and down 2 cycles every second. What's the frequency? 2 cycles per second. What's the frequency? Bob, 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 bob. Yeah, 2 hertz. Oh, one winner, right? So 2 cycles per second is a frequency of 2 hertz, right? Guys, what's the time period between bobs? Half a second, because 1/2 would be half a second. All right, you guys get that?
Yeah.
All right. Who got them points? Hertz, catch up on the points. Wave travels 10 meters in 2 seconds. What's the wave velocity? Wave speed. 10 meters in 2 seconds. You guys do distance over time? 5 meters per second. Right? 10 meters in 2 seconds. That's 5 meters per second. Right? Everybody got that? All right. Very nice, very nice. Oh, for the win. I'll walk you guys through this. Wave has 2 crests, 2 troughs each second. That means it has a frequency of 2 hertz. Okay, so you guys know 2 hertz goes right here, right? Right. If the wave has an average distance 120 meters in 3 seconds, ooh, guys, that's a wave speed of what? 40 meters per second. Right here, got 40 meters per second. Got 2 hertz. What is the wavelength? Can you guys take 40 meters per second and divide by 2 hertz? 20 meters. Look, all right, everybody can do that. All right, all right. All right. Check out the winner's podium. With the bronze, Bella. With the silver, Alexis. And the gold, Hertz Ketchup. Runners up, Kat and Bryn. All right, nice job, guys. Nice job.
Good job.
All right. Back over here. Let's knock out the rest of these textbook problems from chapter 15. And
Wait, no, I don't think
Okay, good to see you. Alright, chapter 15. Alright, so the one we left off on last week was this one with the fire truck. Oh yeah, the Doppler shift. You guys remember Doppler shift? Which is that poster there on the wall. We were able to navigate that. Goes by. Alright, next one, number 71. A vertical tube with the tap at the base is filled with water. There's a tuning fork vibrating over the mouth. Bing. You gotta see this tomorrow. The water level is lowered in the tube. A resonance is heard at 17 meters and also 49 meters, right, between the top of the tube and the water level. What is the frequency of the tuning forks? Actually, this is pretty much exactly your guys' lab tomorrow. I mean, maybe the tiny difference of ignore the tap feel. Here, I'll draw you guys what we're going to do tomorrow. Right, we're going to take a PVC pipe, dunk it in water. We're going to take the pipe up and down. And what happens here? Alright, so here's the PVC pipe. Here's the open end. Tuning fork. Oh, what's going on? Alright, so take that. Oh, oops, zoom out a little bit here. Okay. Alright, when you strike this tuning fork, it's gonna bing. Gonna sing out a single tone. Okay. Oh, we're trying to figure out what that frequency is. Right now, tomorrow, there'll be a number stamped on the tuning fork. It'll say how many hertz it is. Right, but let's say we don't know that. So the question is, what is it? Right, and then I'm going to take this PVC pipe, dunk it in water, and raise and lower it. Now they said instead that this is filled with water, and there's like a tap at the bottom. We're going to let some of the water out. Right? But 17 centimeters. Yeah, 17 centimeters. Can I call that like 0.17 meters? Right? It resonates. And you guys are going to hear this tomorrow. It's going to sound like this. Here, suppose I'm like raising and lowering this this water level. Sound like this. Bing. All right, so it's going to resonate like that. All right, and I can show you guys what's going on with the air molecules. All right, all the air molecules. There's going to be like a high pressure point right here. And that's like lower pressure, and there's like low pressure point up here. Okay? Be like that. Okay. Now, what I just did, that's really hard to do, right? It's really hard to draw all these dots. And also, if you don't do it right, it's really hard to interpret it as a viewer. So it's really common to instead of drawing a true longitudinal wave like I just did, represent that as a transverse wave, which would be like a quarter of a wavelength. Okay? You got like a high pressure here and a low pressure here. Okay? Okay. But your book said there's another place where it also resonates. Okay, and that's not exactly, but approximately 3 times the distance down. So this distance is at 49 centimeters. Right. Guys, what's 17 times 3? 51. 51, right? Which is really close to the 49 centimeters. It's called 0.49 meters, right? Okay. Now, why is it not exactly? Or actually, let me draw some stuff and then go back to that question. Right. So you guys know there's going to be a high pressure point above the water level. Right. You guys know the water level effectively closes one end of the pipe, and this end is open up here. Right. And then we got like a low pressure, and then we're back to like a high pressure here. So I got a high pressure, H for high pressure, L for low pressure. So it's going to go high, low, like that. And let me whip in the rest of this. Remember, there's no true transverse wave going on. This is an abstract idea, right? It's really a longitudinal wave, like all those dots. You can look kind of like that, right? Look at that. So the nodes I'm using to represent high pressure. All right. Now, oh yeah, go ahead.
Is it longer because the sound's traveling fast, so it has a longer wavelength?
Okay, so both those scenarios where it's like and when you down here, it's it's the same frequency and it's the same speed, and it's the same wavelength, right? So all those are the same. Speed, wavelength, and frequency are all the same, right? But I guess you could say like the number of wavelengths is different. Like here it's approximately a quarter of a wavelength, and here it's 3/4 of a wavelength. You guys see that? right? So we got 1/4 wavelength, like lambda over 4, and then 3/4 lambda, right? Now, the top of the tube is not exactly the other location. I think it's like a little bit above the top of the tube is where it actually goes to like the exact fraction, right? And that's why 49 is not exactly 3 times 17. And same thing tomorrow, right? Wherever the top of the other wave is, like the other low pressure point, it's not exactly the top of the tube. The low pressure point is a little bit above it. Right? There's like another equation that goes along with that, but we're going to use this method. We're going to say the difference between these two. Oh, and guys, what is this difference? What is 49 centimeters? Yeah, what is 49 centimeters minus 17 centimeters? Sounds right, 32 centimeters, right? So 32 centimeters, called 0.32 meters, because we're just going to go base SI units, right? Wouldn't that be, how many wavelengths is that? Yeah, half a wavelength, because this is about 3/4 of a wavelength. This is about 1/4 of a wavelength. So wouldn't 3/4 minus 1/4, that'd be 2/4, which is like half a wavelength. This is lambda over 2. Right? Lambda is the wavelength. Right? So if half the wavelength is that, then what is the full wavelength? Be 2 times that, wouldn't it be? Probably call it 0.64 meters. Right? Right. Now, let me backtrack a little bit. Because suppose instead you took this 17 centimeters, you said, well, that's about 1/4 wavelength, so I'm just going to quadruple that. What would that be? Is that 68 centimeters, I think, if you quadruple that? Which is pretty close to what this is. But the method that we did to get 64 centimeters is like more accurate. Right? Take this minus this and then double it. Okay. So we got a 64 centimeter wavelength. You guys get that? Okay. Now the question is, what's the frequency of the tuning fork? So there's actually a piece of missing information, but we're going to make a reasonable assumption. Right. Guys, what piece of information are we missing that we can make a reasonable assumption for? The speed of sound. Yeah, speed of sound. Right? Let's go speed of sound. How about, what do you guys feel like using? 340? Yeah. All right, let's do 340. 340 meters per second. Okay. It depends on the temperature, but that's usually pretty good to go to. Sometimes I use 343. All right. If it's really cold outside, like cold winter day, you might say 331. Let's do this. All right, can you guys say speed is equal to wavelength times frequency? Right? So is frequency equal to speed over wavelength, therefore? Okay. We got 340 about meters per second, which is probably going to be the answer to you guys' lab tomorrow. Tomorrow, I'm going to have you guys calculate the speed of sound, and hopefully it's pretty close to this. And we got 0.64 meter wavelength. The meters cancel, 1/2 is hertz to describe the frequency. See what that comes out to. I'm getting 531 hertz. Yeah, that's what you guys get to, 531 hertz. Right? And being on the temperature and some other little assumptions, you might get plus or minus a little bit, but should be pretty close to that. Okay. All right, so everybody good on number 71? All right. Got 531 hertz. All right, well, we got 2 to go. Number 83, musical instruments. One open organ pipe has a length of 836 millimeters. You guys think we should probably quantify that as 0.836 meters? Just to be safe in our calculations. A second pipe should have a pitch that is a major third higher. How long should the second pipe be? Okay. They kind of draw you guys a picture here. Organ pipes. You guys ever seen organ pipes or pan pipes? I guess same idea or similar idea. See something like this? Okay. Hey guys, if you blow through this one, it's just gonna give you guys a really high pitch or really low pitch. Really low pitch. Right, might be really low pitch. How about this one here? I like really high pitch. Right? Maybe it's like a musical scale. Okay, so we'll get pipes like this. All right, and we got ourselves a root note maybe this is like the root. Okay, let's go to the major third. So like maybe it's like this one, maybe it's like the major third, something like this. Okay. Ooh. So if we're going up, maybe we need a slightly shorter pipe. Okay, something like that. Okay. Right. There's a couple ways we can do this. We can do Pythagorean tuning, or we can do equal temperament. Actually, I think we got time to do both. Let's do both. Let's start with Pythagorean tuning. Pythagorean tuning. Now with that, let me break out the poster that you guys are seeing on the wall anyway. All right, dig through here and find this thing. Here it is. Here it is. Right. Okay. Guys, remember, if you hit these frequency ratios exactly, it's for the major third, it's a 5-to-4 ratio in terms of frequency, right? And so I want the target frequency of the major third compared to the root frequency to be 5 to 4, right? That would sound like a really good harmony. Okay. You guys know speed equals wavelength times frequency, right? Now, the wavelength of the sound of the note and the length of the pipe aren't the same thing necessarily, but I bet they're proportional to each other, right? Maybe maybe it's however you do it, it's gonna be some fraction, it's gonna be proportional, right? And the speed of sound is whatever it is, and we could make up a number like 340 meters per second, but it's the same, right, for all these notes, right? Different wavelengths, different frequencies. So, let's see here. We got new paper, so if I can fit this all here. It's just okay. So I got speed of the third is equal to well, let's say wavelength of the third times the frequency of the third. Okay, and we've got the speed of sound for the root is equal to the wavelength of the root times the frequency of the root. Right? Solved this a little bit different earlier today, but let's try it this way, right? Okay. Got sort of a system of equations here, don't I? System of equations. Okay. Hey, it's okay if you have a system of equations to divide one equation by the other. Right? This isn't the only way you can do it, but you could do that. Okay. So this would be like V over V is 1. Okay. We got the wavelength of the third compared to the wavelength of the root. And then frequency of the third is that, remember we already said that or we know this right here. This right here is a 5-to-4 ratio. This bit right here is a 5-to-4 ratio, isn't it? You guys see that? Okay, pop in right there. So can I say 5-to-4 ratio? Right? Okay. So if I cross multiply the wavelength, right? The wavelength of the now it's the other way around. Well, here, take this fraction up, dunk it upside down, do some cross multiplication. The wavelength of the third is going to end up being 4/5 of the wavelength of the root. Right. Now again, the wavelength and the length of the pipe are not the same thing, but they are directly proportional. Whether you do like whether it's a 1-to-4 ratio, it'd be the same either way, or however you do it. Okay. So the length that we're looking for is going to end up at the end of the day being 4/5 of the original length. This is for the major third. This is the root note, right? Which is in line with the picture that we were thinking. You guys remember we were saying that we want the third to be shorter if we're going up the scale. If we're going up the scale, it has to be shorter, right? And in fact, it's 4/5, right? Again, there's different ways you can do this. There might be like 5 or 10 different ways you can get to the same result. So I just sort of picked one way and went with it, right? So we're going to go with 4/5 of whatever they told us. Actually, we don't even have to worry about millimeter meter conversion. We can just pop this number in. So 836 millimeters. Okay, let's see what that is. So what's 4/5 of 836? 668.8. Now we'll call it 669. How about that? That'd be millimeters. Right? Okay. Now that's using Pythagorean tuning. What I'm kind of curious about is what if instead we went with equal temperament, which has a different formula. So Pythagorean is you're interested in these like exact ratios, which actually sounds best to your ear, right? But modern instruments don't actually use that. Modern instruments actually use equal temperament, and there's a reason for that too. But let's solve that first, then come back to the idea. So the frequency of the third using equal temperament is the root times 2 to the power of n over 12. And the major third is here. The major third is like 4 half steps up from the root. So if you count the number of semitones on the piano, so I'm gonna go 4 over 12 up here. So yeah, what would this be? What's 2 to the power of 4 over 12? Right, so this bit right here is 1.2599, right? Now, actually, let me do kind of a shortcut here. Because remember, before it was 5 over 4, which is 1.25 exactly. I just kind of cut into that point. You just kind of feed it into some work I already did. So let's go, let's just jump straight down to here, right? So the length we need for the third is equal to the original length times 1 over 1.2599, right? We got 836 millimeters. Under 1.2599. All right, so 836 over 1.2599. Okay. So we're looking at 663.54. Maybe I'll round it up a little bit. 664 millimeters, let's call it. Okay. Ooh, interesting. So using Pythagorean tuning, we were getting 669 millimeters. Using equal temperament, which is what manufacturers actually use, it's a little bit short of that, 664, which doesn't sound as good to your ear, that the harmony wouldn't be quite as good. But the advantage of doing this is it's a lot easier to switch keys, right? Versus if you use Pythagorean theorem, or Pythagorean tuning, you're kind of stuck with any key. Okay. All right, you got good? All right, so we got one last one. All right, last one. Okay. 93, guitar strings. Equation for speed of a wave is, well, I'm about to break out a poster, I have the same equation on it. Okay. Guitar string has this mass and it's this long. How many grams, how many centimeters? What's the tension to produce a note that's 147 hertz? All right, let me find that poster. Here we go. All right. So here's all this blown up. Speed of a wave on a string. All right, here's the tension in the string. Mass per unit length. Right. F is the frequency of the note in hertz, right? And the wavelength, well, if you set up a standing wave, it looks like this. Pluck the string. You guys see this is half of a wavelength. So if you take this length and double it, that gets you to the actual wavelength, right? Okay. And so all we have to do is just pop all these pieces together. All right, so 93. They told you mass is 3.2 grams. I'm going to change that to 0.0032 kilograms. Put in base SI units. Okay. They told you the length is 65 centimeters. I'm going to call that 0.65 meters. They told you the target frequency is 147 hertz. So it's like some musical note, right? All right, so let's start by getting the wavelength. How about that? Okay. Here, I think a good way to do this is start at the bottom here and just like feed up and up until we get to this. Okay. All right, so 2 times the length. So 2 times 0.65 meters. 2 times 0.65 meters is 1.30 meters. Okay, so now we know this the wavelength is that long. Okay. All right, now let's take that and feed it into this right here. All right, speed equals wavelength times frequency. Okay. We know wavelength is 1.30 meters. We know the target frequency that was given as we're looking for this musical note, 147 hertz. All right, so what's the speed this wave is traveling on this string? That's 191.1, that would be meters per second, right? Okay, so we got that. Right? All right, and now we can go up to this top equation. Okay, now the question is, what's the tension? Notice I did up sub T for tension force because capital T, well, we got time period all over the place this week, so I'm using up sub T for tension, right? Okay. Hey, could I rearrange this in terms of variables to solve for F sub T? Let's do that. So I could do V squared equals the tension force divided by mass per unit length. Okay, take this mass per unit length and cross multiply it. So the tension force is speed squared times mass per unit length. Right? Just like that. Right? Now let's just pop in all the numbers. Right? We got 191 meters per second. That's right here. Square that. Right. The mass of the string was given as 0.0032 kilograms. And the length of the string was given as 0.65 meters. Did a little conversion to get there. Remember to convert to base SI units. And now it's really important we have those base SI units so we get an answer in newtons. Okay. 191 squared times 0.0032 over 0.65. Okay. I'm getting 179.6 newtons. Yeah, I'll write that. 179.6 newtons. How about that? Okay. So that's how much you right. So as you're tuning that string, right? Tuning string. I think it looks pretty reasonable because here, guys, this right here, this has the gravity force down on it right now of how many newtons? 10, right? Pretty close to 10. So suppose I had a good car string hanging from the ceiling. I had like 18 of these. That's what that would be, right? Like 18 of these. Yeah, I can believe that. That looks pretty believable. All right. So now you guys got your homework knocked out. Yeah, so we got open notes quiz in a couple of days, but we're going to do a lab tomorrow. So if you want to hang on to that and use that as part of your notes, then that's all good.